first example then, the car increases its velocity, so we could write down what we know, and I would always maybe recommend that. So it increases its velocity from 5, so the initial velocity is 5 meters per second, to 25 meters per second, and the time it takes to do that is 8 seconds. We've got to determine the distance travelled and the acceleration of the car. So first of all, Daniel suggests that we calculate the acceleration first. So from this information, I wonder if this is going to work now, from this acceleration, what formula would you use then, Dan? Okay. So we could calculate acceleration. Straight formula, A equals V minus U, 25 minus 5 over 8, which is 20 over 8, which is 2.5 unit meters per second squared. 2.5 meters per second squared. If we look at this thing starting at 5 meters per second, and then after 1 second it's accelerating at the rate of 2.5 meters per second squared. 2.5 meters per second is the way to think of that. That means it's accelerating and it's increasing at the speed at the rate of 2.5 meters per second every second. So if it starts at 5, after 1 second it's going at 7.5. After 2 seconds it will be going at 10, add another 2.5. It's increasing at the rate of 2.5 every second. So after 3 seconds, and then 15, and then 17.5, and so on. And you'll find that after 8 seconds, it's going at 25, which is what we had in the problem. Okay, so it's worth remembering what this actually means. It's not always obvious what this means, meters per second squared. It's a shorthand way of saying it's accelerating at the rate of 2.5 meters per second every second. What about if this was a negative 2.5 meters per second? What would that mean? Minus. Right, so negative means a deceleration, negative acceleration we say. So it's reducing its speed by 2.5 meters per second every second. Okay. So we've got the acceleration, and the next thing we need to do is find the displacement. So how do we find the displacement? What formula would you use? So for the displacement, S equals ut plus a half at squared. Because we know the time, we've now calculated the acceleration, and we know u. So the displacement equals u, which is 5 times 8 plus the acceleration is 2.5 times 8 squared over 2, or 0.5 times that. What does that turn out to be? So 120 meters. So we found the acceleration, and we're using that information, that acceleration, to then find the distance travelled. That's the flaw in this particular method, Daniel, is that we're using something we've calculated to find it. So we've made a mistake in the acceleration. We're going to make another mistake when we come to finding the displacement. Agreed? Is there a way that we can find that displacement from the information given without having recourse to find the acceleration first?
You rearrange the first equation mentioned equals g plus 18.
Yep. But no, without finding A, is there a way to find the displacement without finding A? If we look back to here, oops. This one here is a formula we could use, look. Can we find the average velocity? Yes, it's u plus v over 2, isn't it? So find the average velocity and then use this formula because the average velocity gives displacement over time. So the displacement is going to be the average velocity times the time. So that, in fact, gives us another formula that we can add to our list if we like. Also, displacement S equals the average velocity, which we've written effectively, but if we write it in terms of u plus v over 2 times the time. So we could have calculated it that way. So if we use that in this example, if we go back to the example, wherever it is, what have I done here? Or, for the displacement, S equals average velocity, which is u plus v over 2 times the time, which is going to equal 25 plus 5 over 2 times 8, which hopefully you'll find gives you the same answer. 30 over 2 is 15 times 8 is 120. So that's often the case with these problems. There is more than one way to solve the problem. And so there's no right or wrong way to do it. The only thing to take into account is if you're using one piece of information that you've calculated, further on in the problem, you've got the problem that you might, if you made a mistake, that mistake is going to be carried through. Obviously, sometimes you have to do that, but if you can avoid it, do so.